The disposal of wastewater sludge. The disposal of wastewater sludge is a critical component of modern sanitation, environmental protection, and municipal infrastructure management. As urban populations grow and industrial activities expand, wastewater treatment plants generate increasing volumes of sludge that must be processed, stabilized, and disposed of in a safe, sustainable, and economically viable manner. Effective sludge management not only reduces environmental risks but also enables resource recovery, contributing to a circular economy. Point 1. Understanding wastewater sludge. Wastewater sludge is the semisolid byproduct generated during the physical, chemical, and biological treatment of domestic and industrial wastewater. It typically contains organic matter, microorganisms, pathogenic and non-pathogenic, heavy metals, nutrients, nitrogen and phosphorus, trace contaminants. The characteristics of sludge vary based on the source of wastewater, treatment processes, and conditioning methods. Because untreated sludge poses environmental and public health risks, it requires careful management before final disposal. 2. Stages of sludge processing before disposal. Before sludge can be safely disposed of or reused, it undergoes a series of treatment steps to reduce volume, remove pathogens, improve stability, and minimize environmental impact. 2.1 Thickening. Sludge is concentrated to reduce its water content, typically through gravity thickeners, flotation, or mechanical systems. This step decreases the overall volume and reduces downstream processing costs. 2.2 Stabilization. Biological or chemical processes are used to break down organic materials and destroy pathogens. Common stabilization methods include anaerobic digestion, aerobic digestion, lime stabilization, composting. Stabilization reduces odors, improves handling, and prepares the sludge for further treatment. 2.3 Dewatering. Mechanical equipment such as filter presses, centrifuges, and belt presses removes additional water, converting sludge into a drier, more manageable cake suitable for transport or disposal. 2.4 Drying and incineration. Optional, heat-based methods further reduce volume, destroy pathogens, and sometimes recover energy. Thermal drying produces a product with lower mass, while incineration reduces sludge to inert ash. 3. Methods of wastewater sludge disposal. Municipalities, industries, and environmental agencies use several disposal strategies depending on regulatory standards, economic considerations, and local environmental conditions. 3.1 Land application. Agricultural use. Stabilized sludge, also known as biosolids, can be applied to agricultural fields as a nutrient-rich soil conditioner. When properly treated, biosolids offer nitrogen and phosphorus supply, organic matter enhancement, soil structure improvement. However, strict regulations govern land application to prevent contamination with heavy metals or pathogens. 3.2 Landfilling. Dewatered sludge is often disposed of in sanitary landfills. Modern landfills are engineered to prevent leachate contamination and methane emissions. Limitations include high costs, space constraints, and concerns over long-term environmental impact. 3.3 Incineration. Incineration reduces sludge volume by up to 90% and destroys harmful pathogens and chemicals. Energy recovery is possible through heat and electricity generation. Although environmentally effective, incineration is capital-intensive and generates emissions that require advanced control systems. 3.4 Ocean disposal, largely banned. Historically, some regions disposed of sludge in oceans. Due to significant ecological damage, this practice is banned in many countries. 3.5 Composting. Blending sludge with organic materials such as sawdust or yard waste and allowing it to decompose produces high-quality compost. Composting is cost-effective, environmentally friendly, and suitable for agricultural and landscaping applications. 3.6 Recycling and resource recovery. Modern wastewater management emphasizes energy and nutrient recovery. Key innovations include biogas production from anaerobic digestion, phosphorus recovery through struvite crystallization, production of construction materials like bricks or cement additives. These methods reduce disposal costs and promote sustainability. 4. Environmental and public health considerations. Improper sludge disposal can lead to groundwater contamination, soil pollution, pathogen transmission, odor nuisances, air pollution from incineration. To mitigate these risks, governments enforce environmental regulations such as standards for pathogen reduction, permissible limits for heavy metals, monitoring of land application sites, requirements for emissions control. Compliance ensures public health protection and environmental sustainability. 5. Challenges in sludge disposal. The disposal of wastewater sludge remains a complex and evolving challenge due to rising sludge generation from urbanization, high treatment and transport costs, limited availability of safe disposal sites, increasing public concerns regarding odors and pollution, new contaminants like microplastics and pharmaceuticals. These factors require integrated, innovative, and adaptive solutions. 6. Future directions and sustainable approaches. The future of sludge management is shifting towards circular economy principles that focus on our resource recovery, energy, nutrients, construction materials, advanced thermal technologies, pyrolysis, gasification, decentralized treatment systems, green infrastructure integration, digital monitoring, and automation. Sustainable approaches prioritize minimizing environmental impact while maximizing economic value. Conclusion: the disposal of wastewater sludge is an essential aspect of environmental management and public health protection. Through a combination of thickening, stabilization, dewatering, and advanced treatment, sludge can be transformed from a waste product into a valuable resource. As population pressures and environmental complexities intensify, adopting innovative, sustainable, and well-regulated disposal methods will be crucial. By doing so, communities can enhance resilience, support agricultural productivity, generate renewable energy, and contribute to a cleaner, healthier environment.